Hello, welcome to my talk on continuity equation. In this talk, the focus is the derivation and its applications of continuity equation. Superficially, continuity equation is a simple equation in the fluid dynamics accompanying the Euler equation or Navier-Stokes equation. But in fact, continuity equation is much more important than that. In this talk, I will show how the continuity equation is derived and how we can use the continuity equation in the practical applications other than in the CFD applications. So in this talk, I will discuss what is the continuity equation and how the continuity equation is derived. And I will discuss the continuity equation as a part of the Euler or Navier-Stokes equation. And then I will move to the integral form of continuity equation and its applications. Then the continuity equation for Laplace equation. Continuity equation is a mathematical expression of mass conservation for fluids, one of the basic physical laws of conservation in fluid dynamics. And the continuity equation can be either in different form or integral form. Continuity equation can be very important in fluid dynamics since it could accompany the Euler equation or the Navier-Stokes equation, the momentum equations, to form the complete dynamic equation for fluid motion. It is very important in the practical applications of the Bernoulli's equation, and it would lead the Laplace equation for the potential flows. In the incompressible potential flows, the continuity equation would lead the conventional Laplace equation. And in the compressible flows, the continuity equation could lead to the modified Laplace equation in both subsonic and supersonic potential flows. This will be the topic of my talks in the future. First of all, I would say the continuity equation would be following the derivations of Euler equation or Navier-Stokes equation, which is in the Eulerian approach. This means the fluid element, see here, is fixed in the space, and we will examine how the fluid flows in and flows out of the element. This element would be with the volume delta V equaling to delta X times delta Y times delta Z. Now in here, we will look at the fluid flowed in and flow out the element in Y direction. So the increment of the mass in the element would be given as this. This is the flow-in mass rate, see here, since the direction is with Y. And here we see rho V is the mass flux in Y direction, and rho V times the area would be the mass rate of the fluid. And this part is the fluid mass rate flowing out from the element. So the difference between the flow-in and the flowing out would be the net increase of the mass in the time step delta t. So these two parts would cancel each other, and the expression can be expressed as this. And we can use the volume of the element. So the expression would be given as this for the mass increment in the element due to the mass flow in y direction. In a similar manner, we could calculate the mass increment on that direction. Look at the mass flux rho w on that direction, and the mass increment would be calculated as this. Here, this part is the mass flowing into the element, and this is the mass flowing out of the element. So the difference is the mass increment in the element. Cancel out these two parts, and we have the expression as this for the mass increment due to the mass flux rho w given as this in the time step delta t. And the expression uses the volume of the mass increment at the time step delta t. So, in a similar way, we can calculate the mass increment due to the mass flux on x direction. It is given as this. Now we look at the total mass increment in the element. This would be given delta m equaling to all the mass increment in three directions, delta mx plus delta my plus delta mz. And we should have the increment of the mass in the element given as this. Meanwhile, the mass increment in the fluid element, here in the Eulerian representation, delta V is a fixed value. Thus, the mass increment could only cause the density change of the fluid in the element. Since the mass can be calculated as this rho delta V for the fluid in the element, and the delta m would be caused due to the density change delta rho, so it is given as this. And substitute this into the expression here, we have the expression given as this. So if we look at the expression from the previous slide, we can take delta V out from the expression. Then we have an equation as this. Now if we take delta t is close to t, the limit of delta rho over delta t would be given as the partial differentiation of rho with regard to time t. Why the partial differentiation used here? That because rho could be the function of x, y, and z. Since delta rho is a change due to the time, while the change due to the space are included in this expression in the brackets. Therefore, we put all this together, we could have the continuity equation given in this form. And this is equivalent to an equation as this. And this part is the divergence of the mass flux vector. Now here we will examine a special case when the fluid is incompressible. This means the fluid density would be a constant. As such, we could have the partial differentiation of rho with regard to t is 0 and the rho with regard to x, with regard to y, and with regard to z are all 0. So we look at the continuity equation and we calculate all these terms. Then we have the expression as this. Consider the equations here. We could take this out, this, and this out. So we have the expression as this. Then we have the continuity equation for the incompressible flow given as this. This is equivalent to the expression in a vector form as this. This is the continuity equation for incompressible flow. It is the same as the divergence of velocity vector is 0. Now, we will see how the continuity equation to accompany the Euler equation. As we have shown before, for Euler equation, the moment equations would be given in this form. Here we can see we have 3 moment equations, but we have 4 unknowns: pressure P and 3 velocity components U, V, and W along x-axis, y-axis, and z-axis respectively. So even for the incompressible flow, the fluid density would be a constant. Then we still need an equation. The equation would be the continuity equation. See this. We have the additional equation, but we still have 4 unknowns. This would make a complete Euler equation. 4 equations for 4 unknowns. This could construct a perfect dynamic system. Similarly, for the Navier-Stokes equation, for the incompressible flow, the moment equation would be given as this. And we can see this part of the moment equation is the same as the Euler equation. And this is the extension of the Euler equation with the fluid viscous force. Another difference between the Euler equation and the Navier-Stokes equation is Euler equation is the nonlinear first-order partial differential equation, while the Navier-Stokes equation would be the second-order nonlinear partial differential equation. In a similar way, these 3 equations, we need to solve 4 unknowns: the pressure and the 3 velocity components U, V, and W. Thus, we need the continuity equation to make the fluid dynamic equation complete, and this consists a complete Navier-Stokes equation for incompressible flow. 4 equations for 4 unknowns. Now we will look at the continuity equation in integral form. This can be done by integrate the differential form of the continuity equation to the fluid domain V, given as this. And we write this integral into 2 parts. And the second part on the left-hand side can be changed from the volume integral to the surface integral by using the Gauss divergence theorem, see here, and we can take rho vector v as the vector f. So we have the expression as this. And if we look at this part, vector v dot times vector n, this is the scalar. It's actually the velocity component on the normal vector direction, Vn. And here, the surface integration is on the S, the closed surface including the volume. Now we can examine the integral form of the equation. So this part is the rate of mass change in the fluid domain V. And if we look at the surface integral itself, it can be understood to be the net rate of mass flowing out from the domain. And the negative sign here can be understood this part would be the net rate of mass flow in to the fluid domain V. This is a little bit difficult to understand. However, if we write the integral as this, we move the negative sign for the normal vector n, and we can see minus vector n would be just opposite in the direction with vector n. Now, the understanding of this equation would be this term, the rate of mass change in the fluid domain, and this term would be the net rate of mass flow into the fluid domain, since the minus vector n is pointing into the fluid domain. So this can be easily understood. The integral form of the continuity equation is an expression of the mass conservation. In here, we have a look at the special case for a steady flow. For a steady flow, that means the partial differentiation of density with regard to t would be 0. Thus, the volume integral of the partial differentiation, the density with regard to t, would be 0. Then we could have the integral, the surface integral, this equaling to 0. This equation means for a steady flow, the flow can flow in and flow out to the fluid domain through the surface, but the net rate of mass flow in and flow out the fluid domain V must be 0. That is, the total mass in the fluid domain is a constant, a form of mass conservation. Now in next 2 slides, we will use the integral form of continuity equation for some flow. The first example is the pipe flow. See the picture here. The pipe has 2 different sections, S1 and S2. So in the analysis of the flow, we also include the pipe wall SW into the analysis. And we can see S1, SW, and S2 will make a closed surface S. Therefore, the integral of this would be separated into 3 parts. The integral on SW, the pipe wall, and the integral on the surface S1, and the integral on the surface S2. And here, on the pipe wall, since the velocity vector v and the normal vector n would be orthogonal everywhere, thus this term, the dot product of the velocity vector and the normal vector n would be 0, or simply we understood there is no flow out or flow in through the pipe wall. Thus, this term would be 0. Therefore, we have the equation for the continuity equation for pipe flow given as this. And this term is from the integration on S1. Since on S1, we can consider the velocity density would be uniform. Thus, the integral would be given as this. Here, the normal vector m1 and the velocity vector v1 are in opposite direction. Therefore, minus sign here. And this term is from the integration on S2. Similarly, on S2, the flow can be considered uniform. Thus, ρ2 and v2 would be constant on S2. Therefore, the integration would be given as this. Unlike the on S1, here on S2, the velocity vector and the normal vector of S2 are in the same direction. Thus, the result given as this. So we have the continuity equation for the pipe flow given as this. If we examine the value on both sides of the equation, we can see these values are actually the fluid mass rate. The fluid mass rate past the section area S1 or S2, given as this. This means in the steady flow, the flow mass rate would be a constant, regardless whether the density would be a constant or not. For many practical applications, the flow in the pipe can be considered as incompressible flow. Therefore, we have the density ρ1 equaling to ρ2. Then the continuity equation can be written as this. The velocity times the section area is actually the fluid volume flow rate, Q. So for incompressible flow, the flow rate past the section area S1 and the area S2 would be same, a constant. This expression would be very useful since when we calculate the pipe flow, this is the most used equation for calculating the velocity in the pipe. For instance, in many practical applications of the pipe flow, the flow rate Q is normally given and the section areas S1 and S2 are known. Then we can easily calculate the velocities V1 at S1, V2 at S2. Accordingly, we can further use Bernoulli's equation to find the pressure in the pipe. Here we can see we can only employ the continuity equation to get the fluid velocities, other than solving the actual fluid dynamics equation, the moment equation. But in getting the fluid pressure, we apply the Bernoulli's equation, the integral form of the Euler equation for fluid moment equation of inviscid flows. This simple principle can be used in the pipe flow when the pipe is short and the change of the pipe is smooth. Thus, the fluid viscosity effect can be ignored, as we have seen in the pipe flows of water and air. Both flows have small viscosities. The second example is the fluid stream tube. See the picture here. A stream tube is the bunch of streamline, and on all these streamlines, the density, pressure, and velocity would be uniform. So, similarly, the section S1 and section S2 plus the control surface SC following the streamlines. So these three surfaces would make a closed surface S. For a steady flow, the continuity equation would be given as this. The surface integration on the control surface, the surface integration on S1, and the surface integration on S2. Now this part would be zero, even velocity itself would not be zero, but the vector n on the control surface would all perpendicular to the velocity direction. Thus, this dot product would be zero. The integration would become this equation, and since on S1, density velocity would be uniform, thus we can simply integrate this into this. And we notice the velocity and the normal vector on S1 would be opposite, so we have minus sign here. And on S2, the density, velocity, and the pressure would be uniform. Thus, we have the result for the integral on S2 as this. And again, we have the expression for this. So similarly, for the incompressible flow, the density on S1 and on S2 would be same. Thus, we will have the continuity equation for the stream tube given as V1 times S1 equaling to V2 times S2. Now in the next two slides, the continuity equation would be used for the potential flows. For a potential flow, the velocity vector V is defined as the gradient of the velocity potential function phi. So the vector form of the velocity would be given as the gradient of the lambda phi. This velocity has three velocity components. U is defined as the partial differentiation of phi with regard to x. V is the partial differentiation of phi with regard to y. W is the potential function phi with regard to z. And now, if we apply the continuity equation for the incompressible flow given as this, and the vector form as the zero divergence of the velocity vector. So if we substitute the velocity component of the potential flow UVW into the continuity equation, we have the expression as this and this. Then we can obtain the Laplace equation given as the second-order partial differentiation of the potential function with regard to x plus the potential function with regard to y and the potential function with regard to z. Or in a vector form given as this simple expression, here Laplace squared is the Laplace operator. So we have the simple Laplace equation given as this. So from the Laplace equation, we can see we have one equation, and this is for one unknown, the velocity potential function phi. Now the question is, when we derive the Laplace equation, we didn't apply any dynamic equation, the Euler equation or the Navier-Stokes equation. In deriving the Laplace equation, we only assume the fluid is potential flow and apply the continuity equation for incompressible flows. That means if we solve the Laplace equation, we can obtain the velocity potential function phi, and then we can calculate the velocity component. Then the question would be how this Laplace equation works in fluid dynamics. The answer for this would be solving the Laplace equation and apply the Bernoulli's equation, which is actually an integral form of Euler equation. For example, a potential flow passes an airfoil, which is an important flow. So the solution can be made for solving the Laplace equation by considering the Kuta-Yukovsky condition. Therefore, when we solve the potential function, we didn't apply any fluid dynamic equation, the Euler equation or Navier-Stokes equation. Then once we solve the flow field, the velocity component, then we can apply the Bernoulli's equation for calculating the pressure and the pressure coefficient. Thus, the Bernoulli's equation links the potential flow and the fluid dynamics.